This is AQA GCSE Chemistry. It's a dual and triple award. We're starting on rate and equilibrium. In this first video, we are going to take a look at what we mean when we talk about rate of chemical reaction. We're going to look at the mean rate of reaction calculations and calculations about the rate of reaction at a specific time. The objective about how to collect data will be covered across a range of videos within this topic. But the first thing is to take on board this key information in the blue box. The mean rate of reaction, so that's the average rate of reaction from beginning of reaction to end, is how much reactant has been used divided by time, or how much product has been formed divided by time. So let's look at that. How might that work in practice? I'm going to recommend you pause on any activities and then try them. So in the first instance, we have got 20 centimetres cubed of carbon dioxide produced, and that's happened in 30 seconds. So the amount produced, 20, divided by time, 30, gives us a rate of 0.6 or 0.6 recurring centimetre cubed per second. On the next one, it's about how much sodium has been used up. We used 3 grams in 40 seconds, so the rate is 3 divided by 40, 0.075 grams per second. Now, that tells us the mean rate of reaction, but actually that isn't always useful, because a rate of reaction is not uniform. It doesn't stay the same from beginning to end. It will actually always start off fastest and eventually slow down till it stops, for reasons that we will discuss in later videos. But we can see here that if I wanted to know the rate of reaction at 50 seconds, I'm going to start by drawing a tangent to the line at 50 seconds. Now, from your knowledge of maths, you will know that's a straight line that only touches the curve at that point. From there, you are going to work out what the gradient of the line is, change in y, over change in x. And you can see there, that's 0.7 divided by 100. We get 0.007 grams per second. So there's an opportunity for you to have a go at plotting here, work through the question and see how you do. I'm going to go ahead and plot this as well, and you can see here that I've got my time on the x-axis, 0 to 120, scale worked out pretty nicely there, and I'm going to put my mass of CO2 on the y-axis going all the way up to 1, making sure that I've got enough space at the top in case I'm extrapolating. Now from there I go ahead and I plot the points, and you can see I've plotted with crosses. I'm not using dots because they get lost when you draw the line of best fit, so always use a cross when you do this. And then it's about drawing the line of best fit, which I've done here. That took me 2 or 3 attempts. Sometimes it won't happen immediately. It's good to practice these so you can do them in one smooth sweeping motion. Now we're actually interested in what the rate of reaction is at 60 seconds. So you can see at 60, I have drawn my tangent to the curve. It touches at 60, it does not touch anywhere else. And if I want to know the rate of reaction, I want to know grams per second, or cm cubed per second, then I'm going to need to work out that gradient, and I'm going to use as much of the line as possible. So you can see I've managed to get all the way across and all that way up. That then allows me to work out what the change in y here is and what the change in x is. The change in x is nice and simple. It went from 0 to 100. For this one, reading it, it's gone to 0.95, and we started at 0.4, so it's an overall change of 0.55. Now we have a slight problem here. You will have noticed I have made an error on this graph. There's something that's missing, and it makes it harder to show what you know. I've correctly labelled the x-axis, but I didn't label the y-axis. So I've put that one on now, mass of CO2 in grams. My rate of reaction is therefore change in y over change in x, which is 0.55 divided by 100, giving me a rate, not an average rate, not a mean rate, but the actual rate after 60 seconds of the reaction had elapsed, is 0.0055 grams per second. That takes us to the end of this video. Thank you for listening, and goodbye.